principle of different sensors. Okay. Now let us continue the different types of sensors working principle. Okay, today now let us discuss the optical sensor. Okay, the optical sensor is also called as electro-optical sensors. These sensors are electronic detectors. These sensors are electronic detectors that convert light or change in light into an electronic signals. Okay, so these are all the electronic detectors that will convert light or a change in light into an electronic signal. So these sensors are able to detect electromagnetic radiation from the infrared up to the ultraviolet wavelengths. They are used in many industrial and consumer applications. For example, lamps that turn on automatically in response to the darkness, and the position sensors that activate when an object interrupts a light beam. And next is flash detection to synchronize one photographic flash to another. And next is photoelectric sensors that detect the distance, absence, or presence of an object. These are all some of the applications of the optical sensors currently used in many of the places. Okay, in automobile we are having the sensor. The purpose for having the sensor is position to identify the positions. So positions is going to be identified. The position sensors that activate when object interrupts a light beam. Okay, for that purpose we are using these optical sensors here. Okay, in a sufficiently clean environment, shaft positions can also be sensed using optical techniques. So here we are having some other figures, so we can able to see the figures how it is going to work. So here the magnetic system and the disk is directly coupled to the crankshaft. So this time the disk has holes. Disk has holes in it that correspond to the number of tabs on the disk of the magnetic system. Okay, then it is mounted on each side of the disk or fiber optical light pipes. Okay, the hole is in the disk allows the transmission of light through the light pipes from the light emitting diode source to the phototransistor used as light sensor. Here the light would not be transmitted from source to sensor when there is no hole because the solid disk blocks the light. Okay, and then you can see the figures. So here the pulse of the light is going to be detected by the phototransistor. So here we are using a phototransistor. So these are all the important parts. So this is a shaft. So the rotation of disk is going to causes alternate blocking and the transmission of light. Okay, this is a sensor disk. This disk has holes, many holes. And here we are having the light emitting diode, fiber optic light pipe we are having. So when it is going to rotates, so when this rotation is going to reach the fiber optic light pipe, so the light is going to be emitted inside. Then then we will receive the electronic signal. So that signal is going to be amplified from the amplifier. Then it is going to transmitted to the amplifier. Okay. So when the hole is going to get passed, when hole is going to get reached, so here the light is going to pass us, then signal is going to be immediately received. Okay, and this is the working principle of the rotation of the optical sensor. So the optical sensor is going to convert light rays into electronic signals. So here the light rays is going to pass over these holes, and then it measures the physical quantity of light and then translates it into a form that is readable by an instrument. An optical sensor is generally part of larger system that integrates a source of light, a measuring device, and the optical sensor. Okay, this is often connected to an electrical trigger. This trigger reacts to a change in the signal within the light sensor. An optical sensor can measure the changes from one or several light beams. Okay, when a change occurs, the light sensor operates as a photoelectric trigger and therefore either increases or decreases the electrical output. Again, an optical switch is going to enable signal in optical fibers or integrated optical circuits to be switched selectively from one circuit to another. Okay, an optical switch can operate by mechanical means or by electro-optic effects, magneto-optic effects, as well as by other methods. Optical switches are opto-electronic devices which can be integrated or discrete microelectronic circuits. The types of optical sensors, there are many different kinds of optical sensors. The most common types are photoconductive devices, that is going to convert a change of incident light into a change of resistance. And next is photovoltaics, that is commonly known as solar cells. So it will convert an amount of incident light into an output voltage. And next is photodiodes, so it will convert an amount of incident light into an output current. And next is phototransistors. So this phototransistor are type of bipolar transistor where the base collector junction is exposed to light. So this result in the same behavior of a photodiode, but with an internal gain. So in this, optical switches are usually used in optical fibers. So where the electro-optic effect is used to switch one circuit to another. Okay, these switches can be implemented with, for example, micro electromechanical system or piezo electronic system. Okay, so these are all the important thing of the optical sensor. Okay, next, so we can discuss about the throttle position sensor. Okay, why we want to have the throttle position sensor? Okay, the throttle, for example, you are going to drive an IC engine equipped automotive vehicle, so you are going to use your foot or hand to accelerate your throttle. When you are going to rotate or press it, so the throttle valve is going to get opened. So depends upon the varying load condition on your vehicle. Okay, according to that, so the here we are using a throttle position sensor. So when you are going to press or when you are going to rotate it, the throttle valve is going to get opened in some particular angle. So in R&D department, so already they have programmed. So for example, how much the angle of the valve is going to get open. So how much quantity of or how much amount of air fuel mixture is going to require to operate the IC engines in the varying load conditions. So that is calculated by the R&D department. So that is programmed in the microprocessor or controller. So this is what happened. So this throttle position sensor is shortly called as TPS. TPS, throttle position sensor. So this is going to monitor the air intake of an engine. The sensor is usually located on the butterfly spindle shaft, so it can directly monitor the position of the throttle. More advanced forms of the sensor are also used. For example, an extra closed throttle position sensor, that is a CTPS, may be employed to indicate that the throttle is completely closed. So some engine control units, ECUs, or electronic control units also control the throttle position, electronic throttle control, or drive-by-wire system. So, and if that is done, the position sensor is used in a feedback loop to enable that control. Okay, related to the TPS or accelerator pedal sensor, so which often include a wide open throttle, so that is WOT sensor, so that accelerator pedal sensor used in electronic throttle or drive-by-wire system. So the modern sensors are non-contact type. So these modern contact TPS include Hall effect sensors, inductive sensors, magneto-resistive, and other sensors. So in the potentiometric type sensors, a multi-finger metal brush brake is in contact with the resistive strip. So while the butterfly valve is turned from the lower mechanical stop to WOT, so there is a change in the resistance, and this change in resistance is given as the input to the ECU. So non-contact type TPS work on the principle of Hall effect or inductive sensors or magnetoresistive technologies, wherein generally the magnet or inductive loop is the dynamic part which is mounted on the butterfly valve throttle, spindle, shaft gear, and the sensor and signal processing circuit board is mounted within the ETC gearbox cover, and it is stationary. So now let us see the working principle of this throttle position sensor. Okay, the sensor is usually mounted on the throttle body, so it senses the position of the throttle valve or butterfly valve, and it will transmit the information to the engine control unit. So this is the important function of the throttle position valve, electronically controlled throttle position valve (TPS). So the sensor monitors how far down the accelerometer pedal is pushed and gives the output current determining the position of the pedal. Okay, you just listen this once again. So the sensor monitors how far down the accelerometer pedal, so that is pushed, and gives the output current determining the position of the pedal. The position of the pedal controls the airflow of the engine. If the valve is wide open, the large amount of air is going to supply to the engine and vice versa. So the output given by the sensor along with other sensor is transmitted to the engine control unit, so which decides the amount of fuel to be injected to the engine accordingly. The sensor is a three-wired potentiometer. So we just look into this picture. So through the first wire, the 5-volt power is supplied to the sensors resistive layer. The second wire is used as a ground, whereas the third wire is connected to the potentiometer wiper and provides input to the engine control system. So based on its construction, there are three types of throttle position sensors. They are the throttle position sensor, which build in end switches, also known as closed throttle position sensors. The potentiometer type combination of the both type sensors. So the applications, this sensors gives the engine control unit information about the position of the butterfly valve, and then it is used to detect the ideal position, wide open throttle state of the valve. So when in valve is in ideal state, the output voltage of the sensor is below 0.7 volt. So when the full load state is detected, the output voltage is of the sensor is about 4.5 volt. So everything is just variation of the voltage variations when you are going to pressing the pedal, accelerator pedal, or when you are going to rotating. So depends upon that the voltage signal is going to transmit it to the ECU. So based on that, the ECU will give some signals to the actuators. So that actuators will take care of the torque, how much amount of the air is required or fuel is required. So that is going to taken care by the actuators. So these are all the important functions.
Hi, I'm Matt from TPSTool.com. We talk a lot about adjusting the throttle position sensor, or TPS, but I thought it'd be interesting to talk about what it actually does and how it works. So on any engine, to get the best performance, you've got to have the right mix of fuel and air. The computer that calculates how much fuel to put in needs to know how much air is going in the motor. So one of the sensors it uses is a throttle position sensor, and that sensor tells the computer how far the throttle is open. To give you an example, I've got our TPS tool ProMeter here connected to a throttle body system from KTM. And you'll notice the number on here, 0.46, that's at idle. So as I open the throttle, watch the throttle plate and watch the numbers increase. This is what the computer sees. So you can see as I open the throttle, all the way to full throttle, the numbers rise steadily. And that's what the computer uses to determine how far open the throttle is. And the way it works is actually really simple. It's just a variable resistor. There's a shaft that goes through the throttle plate and into the throttle position sensor. And I will show you. So all it is a shaft with a square edge on it. And as the throttle plate rotates, the shaft rotates. And that turns the inside of the throttle position sensor. And when you turn the inside, it changes the resistance. So let's show you how that actually works inside. Okay, 10-second electrical tutorial. Now we've got a twisting motion. We need to convert that into a voltage. How do you do that? Well, you need to know one basic thing about electricity. Pencil lead is actually a conductor, and it's a great material to use for this example. So when you flow electricity through a wire, it loses energy along the way, and as a result, the voltage drops. And so what you can do, when you want to know check the voltage flow current through this across our circuit. So now we have a current flowing through our piece of paper, through our pencil lead. Check over here, you'll see we've got 5 volts. Now watch. As I move my probe down the circuit, what's happening? The voltage is dropping, right? So what's actually happening is as the current moves through the pencil lead, it's losing energy. It's giving off some heat. And that results in the voltage dropping. When I get all the way over here, we're at 0, right? Move up. So this would be about half throttle-ish. Move all the way to full throttle. So this is exactly how the throttle position sensor works. There's a mechanical wiper that moves up and down a piece of material that has current flowing through it, and the wiper is used to read the voltage at that location. And that's how we convert a mechanical position to a voltage that the computer can read. So let's dive into the real thing and take a look at how it works. Okay, what we've got here is a real honest-to-goodness throttle position sensor. I spent some time alone with it in a Dremel and took it apart so we can see how it works. So we get rid of the cover. We've got a spring here that we don't need anymore. And right inside, we can see this is the circular wiper that we talked about that rotates when you turn the throttle. And so let's see how it actually works. Let's plug it into our Pro meter here. Give it 5 volts. There we go. And now there's no return spring, so it's not going to return automatically. But you can see we're at 0.7 volts now. And as we rotate this, voltage is going to go up. Rotate it back, it's going to go down. As you twist the throttle, that's what happens. So now let's see what's actually inside this thing. So this is the wiper we talked about. And you can see it's just a thin piece of metal. It's actually 2 pieces of metal. It connects the conductor we were referring to a different conductor that reads the voltage. And so let's take a look. Those are tiny little fingers. And that's important. They do it that way so that it doesn't lose contact while you're bouncing through the whoops or hopping over things. And when we look inside here, what's that? That is the circular conductor that we spoke about earlier. And it's on a flexible circuit board, essentially. And so what you've got is these lighter colors are wires called traces and a circuit board. This is essentially a flexible circuit board. And this section here is the flexible conductor we were talking about. So this wire runs power through this conductor. And as the current runs through the conductor, it loses voltage all the way across. So on this side, it's going to start at 5 volts. On this side, it's going to have essentially no volts. And it's going to lose all the way across. So let's take a look. I've got my meters connected since this one has a probe. So it'll be easier to use for this example. So watch, as I touch over here, I had them backwards. This is the 0 over here. As you come this way, that's full throttle, essentially 5 volts. And as I go back, you know, half throttle, you're somewhere in here. And as you go across this conductor, the voltage changes because the electricity loses energy, loses voltage as it goes across the conductor, as the resistance eats it up. So that energy is actually lost in the form of heat, but there's such a tiny amount of current that goes across that you really couldn't measure it. So let's see if we can do it now. Come back here since it's all connected and use our wiper. Maybe I can do the wiper. So what this actually does is connects the part of this conductor that we're interested in reading with the second conductor. And the second conductor is just for reading. It doesn't, practically no current flows through the second one at all. It's all just for voltage. So this is the one that current flows through. So we'll take our wiper here and see if we can do this manually. My fingers aren't too fat to be in there. So there we go. And as we slide it across, there we go. We slide it back down the aisle, right? So when a TPS goes bad, usually what happens is, you know, something, one of these wipers, something will happen to it, or something along this conductor will either get worn out and chip off, or maybe it'll get some dirt in there and it won't conduct all the time. You know, these wipers will touch the dirt and they won't make good contact or something like that. But I thought you guys would find this interesting, that it's just that simple. It's not complicated at all. And I hope you enjoyed this. Thanks. Bye-bye.
Okay, guys, I think suppose if you have seen this video, I think you have clearly understood how the voltage was varies. Okay, because I am theoretically telling, so when you are going to pressing, so the voltage is going to vary, the signal is going to send it. But in this video, so I think you have practically seen how he was changed the voltage and how he explained the voltage variations. So when you are going to pressing or when you are going to when the wall position is going to changes. So guys, the next topic is thermistor. The thermistor is used to the thermistor and the temperature sensor. So everything is going to use to measure the temperatures. So the temperature is going to measure because in IC engines we need to measure the lot of temperatures and that. Uh, just a minute. Okay, guys, because in four-wheeler and any kind of two-wheeler, so I think nowadays the most of the latest vehicles equipped with the temperature sensors, and you can able to see the temperature of your engine and as well as the air cooler AC temperature. Also, you can able to see in your dashboard what is the amount of temperature is going to generate in your IC engine. So that is also you can able to see in dashboard, as well as your air conditioning system of your automotive vehicles is also you can able to see it. Because of the so many devices used in the IC engine, so you can able to identify the temperatures. Okay, thermistor is a resistance, is a resistance thermometer or a resistor whose resistance is dependent upon temperature. So the term is combination of thermal and resistor. It is made of metallic oxides pressed into a bead, disc, or a cylindrical shape, and then encapsulated with an impermeable material such as epoxy or glass. Okay, in this there are two different types of thermistors we are using. So the two types of thermistors you can see here, the negative temperature coefficient, okay, the NTC coefficient, negative temperature coefficient and positive temperature coefficient. So that is PTC. With an NTC thermistor, when the temperature increases, the resistance is also decreases. Conversely, when temperature decreases, the resistance increases. So this type of thermistor is used most. So once again, I repeat you. So with an anti-heat thermistor, when the temperature increases, the resistance decreases. Conversely, when the temperature decreases, the resistance is increases. So this type of thermistor is used the most. In PTC thermistor works a little differently when we compare it to the NTC, negative thermal coefficient. In PTC, the thermistor works a little differently. When temperature increases, the resistance increases. When temperature decreases, resistance decreases. So these type of thermistor is generally used as fuse. Okay, I think you can understood. When temperature increases, the resistance increases. When temperature decreases, resistance decreases. So this type of thermistor is going to use in a fuse. Typically, the thermistor achieves high precision with unlimited temperature range of about 50 degrees Celsius around the target temperature. Okay, this range is dependent on the base resistance.
Hi folks, I'm going to talk about a little electrical component for measuring temperature called a thermistor. I originally needed it for measuring the water temperature in a set of experiments, determining if cold water boils faster than hot. But just for fun, I also got it to turn on this PC fan when the heat was too high. What's a thermistor? A thermistor is usually a ceramic or polymer material with two wires connected to it. The key is that the thermistor's resistance changes with temperature. With some, the resistance increases as the temperature increases. Those are called positive temperature coefficient, or PTC thermistors. With others, the resistance decreases as the temperature increases. Those are called negative temperature coefficient, or NTC thermistors. I couldn't find a thermistor locally, but some quick research turned up that automobile coolant temperature sensors are just thermistors in a protective case, which was a good thing since that saved me having to make a case of my own. With this one, there's only one obvious place to connect to, this threaded part. So where do the two thermistor wires go inside? Well, one goes to the threaded part and the other goes to the brass case. So I wrapped one wire tightly around the case And after attaching a ring terminal to a wire and finding suitable nuts, I attached another wire to the threaded part. I then connected up a meter and put it on the resistance scale. Remember, the resistance changes with the temperature. I put my fingers on the probe part and it started to heat up. Sure enough, the resistance on the meter started to decrease as the temperature increased. So it contains an NTC, or a negative temperature coefficient thermistor. To be useful, I needed to know what resistance matches what temperature. Unfortunately, I couldn't find a resistance temperature table for this particular one, so I had to make my own. To do that, I prepared a tall container, this soda can with all the paint sanded off. I filled it with water and put the probe part of the sensor in the water. I also put in my kitchen thermometer. The long length of my thermometer is why I went with a tall container. For my purposes, I needed to know the resistance to temperature values for temperatures near the freezing point of water. So I put the whole thing in my freezer until the thermometer read near 0 Celsius, or 32 Fahrenheit. Then I took it out, connected my meter to measure resistance, and put it on my stove heating element. I then started recording the resistance on the meter and the corresponding temperature on the thermometer as the stove element heated up the water. I stopped once it reached boiling, which is 100 Celsius or 212 Fahrenheit. And here's the chart drawn using the data from my table. As you can see, the resistance decreases as the temperature increases. You can also see that it's a curve. The whole reason I'd gone through this process was to do some experiments to determine if cold water boiled faster than hot water, as some people think it does, and to find out why that myth might exist. That resulted in this graph of water temperature as it was heated up over time. But that's a whole other topic, which I cover in another video I'll point out later. Here's the fun I had making a PC fan turn on when the thermistor gets too hot. First, here's the circuit without the thermistor. It's very simple. The positive from my homemade power supply goes to the positive of the fan, and the negative of the fan goes back to the power supply. When I turn on the power supply, the fan starts spinning. Now here it is with the thermistor. The positive from the power supply goes to one end of the thermistor. The other end of the thermistor goes to the positive of the PC fan, and the negative of the PC fan goes back to the power supply. But this time, when I turn on the power supply, the fan doesn't start spinning. That's because the thermistor is nice and cool at room temperature, and so it has a high resistance. The fan needs a certain amount of electrical current going through it in order to spin. But the higher the resistance in the thermistor, the lower the current is going through the fan. And the resistance of the thermistor is high enough to make that current too low. Now I use this hair dryer to heat up the thermistor. That causes the thermistor's resistance to decrease. As it decreases, the current increases. And when the current's high enough, the fan starts spinning. Notice that the fan is blowing on the thermistor, making it cool off more quickly. Here I'm showing the airflow direction using this tissue paper. As the thermistor cools, its resistance increases, and that causes the current going through the fan to decrease. After a minute or so, the current is too low to keep the fan spinning, so it stops. Well, thanks for watching.
I think once again you have clearly understood the practical demonstration of thermistor and how it works. So I think it's a fantastic video. He explained briefly how the thermistor was working. So practically, I think you have understood about the thermistors. Okay, now let us discuss the temperature sensor. Okay, first of all, you have questions. What is a temperature sensor and where it is used? Okay, the temperature sensor is a device used to measure temperature. So this can be air temperature, or liquid temperature, or the temperature of solid matter. Okay, there are different types of temperature sensors available, and they can use different technologies and principles to take the temperature measurement. Okay, the different types of temperature sensors are, as we see previously, the thermistor and resistant temperature detectors and thermocouples and temperature probes. Okay, and these are all the different types of temperature sensors. What is a temperature sensors used for? Temperature sensor are used to measure temperature in many different applications and industries. They are all around us, present in both everyday life and more industrial settings. Some applications are industrial applications, monitoring various machinery and environments, power plants, manufacturing. Scientific and laboratory applications, science and biotech monitoring. Medical applications, patient monitoring, medical devices, gas analysis. Okay, and humidifiers, ventilator flow tubes, and these are all some of the examples. And motor sports, exhaust gas, inlet air temperature, oil temperature, and engine temperature measurements. And next is domestic applications, kitchen applications, oven, kettles, as well as white goods. Next, HVAC applications, heating, ventilation, and air conditioning devices, either commercial or domesticated. These are all some of the applications where this temperature sensor is going to be used in practical.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at contact temperature sensors to understand the different types and the basics of how each one works. We'll look at the main types being the thermocouple, the RTD, and the thermistor. If, after watching this video, you want to learn even more about temperature sensors, then I recommend you head over to Danfoss Learning and check out some of their e-lessons. They have self-guided online courses that will take you deeper on both the technology and the theory behind temperature sensors. The e-lessons are absolutely free, so just use the link in the video description down below to head over to the Danfoss Learning site and create your account today. So how do we physically measure temperature? We all know we can measure temperature using a thermometer. This is a very basic design used for hundreds of years. It's simply a sealed glass tube which is partly filled with some liquid like mercury or alcohol. As heat is applied, the liquid expands and rises up the column. The height of the column is divided up and marked to correlate it with known temperatures. For example, water boils at 100 degrees Celsius and it also freezes at 0 degrees Celsius. So as the liquid expands and contracts, we can easily read the temperature. This method is easy for humans to use, but it's slow, it's not the most reliable or accurate, and we're pretty limited on temperature range. So we need a fast and accurate way to take digital temperature readings, which will allow computers and controllers to accurately monitor and autonomously control systems. So how can we take accurate digital temperature measurements? The oldest way to do this is to use a thermocouple. If you have a handheld temperature probe or even a multimeter which can take temperature readings, it's probably going to use one of these. But these are also built into solid cases like this for a much more rugged design. With a thermocouple, we connect two different metals together at one end and the other end connect into a terminal block. Then we basically use a voltmeter to read the voltage difference between the two. The voltage here will be very tiny. So how does this work? Let's say we held a metal rod in our hand and placed the other end into a flame. We know that the rod will heat up and this heat will travel along the length of the rod and up to our hand. What's happening here is the heat is exciting the atoms and molecules which form the material structure. The heat causes the molecules and the atoms to vibrate. The vibration is so tiny that you can't feel it in your hand. The excited atoms will allow their free electrons to move more easily and they will move towards the cooler end of the rod. This only occurs because there is a temperature gradient, a difference in temperature from one end to the other. So at the cooler end, we'll have slightly more electrons than the hotter end. And as electrons are negatively charged, we therefore get a slightly negative and positive charged ends of the rod. Voltage is like pressure. When we measure voltage, we're measuring the difference or potential difference between 2 points. If you imagine a pressurized water pipe, we can see the pressure using a pressure gauge. The pressure reading is comparing 2 different points also. The pressure inside the pipe compared to the atmospheric pressure outside the pipe. When the tank is empty, the gauges read 0 because it has nothing to compare. Both are the same pressure. Same with voltage. We are comparing the difference between one point to another. If we read across a 1.5 volt battery, we get a reading of 1.5 volts. But if we try to measure the same side, we wouldn't read any voltage. We can only measure the difference between 2 points. Coming back to the thermocouple, if we connected 2 wires together and they were of the same material, let's say they were made of copper, and we applied heat to one end to create the temperature difference, then the electrons would scatter and build up at the cold ends, but they would build up in equal amounts in each wire because they are the same material. This means that they will both conduct heat equally and the temperature gradient is going to be the same. Therefore, our voltmeter wouldn't be able to measure any difference. However, if we connected 2 wires which were made of different materials, let's say one was made from copper and the other one made from iron, then the 2 metals would conduct heat differently, so their temperature gradient will be different. That means the electron buildup at the cold ends will also be different. So, if we now connect our voltmeter to this, then we can read a voltage difference. So to make this into a useful tool, we just calibrate it by testing the device against known temperatures, and then we mark down the voltages generated. Then we'll use a formula to tell the temperature from the voltage. For this to work best, we should submerge the cold junction into an ice bath. That way we get a voltage with a reference relative to 0 degrees Celsius or 32 degrees Fahrenheit. Remember I said that with pressure in a pipe, we are comparing it against the atmospheric pressure outside. That's because we know the pressure outside the pipe is atmospheric pressure. So for the voltage reading to be accurate, we need to measure against something we know. So we use ice water because we know this temperature is constant at 0 degrees Celsius or 32 degrees Fahrenheit. This method is mainly used in science labs. However, this isn't very practical for most engineering applications. So instead, to improve the accuracy, we leave the cold junctions at an equal ambient temperature, and then we compensate this difference by measuring the temperature of the connection and applying a formula to offset the error. To measure the temperature of the connection, we often use an RTD temperature sensor, which we're going to look at next in this video. This is also a fairly simple design, probably easier to understand than the thermocouple. They usually come in these type of designs for engineering applications with much more rugged casing. So how do these work? Well, we know that electricity is the flow of electrons through a circuit. We've covered this in great detail in previous videos, links down below for that. When we pass electricity through a material, let's say a copper wire, the material will have some resistance to the flow of electrons. And we can measure this resistance with a multimeter. Different materials have different resistance levels. The temperature of the material will change the resistance of the material. Most conductors will increase in resistance the hotter they get. That's very typical of metals. This occurs because as the atoms and molecules become excited, they move around a lot, so it's harder for the free electrons to get through without a collision. So using a formula known as Ohm's law, voltage is equal to current multiplied by resistance. This means that as long as we keep the current the same, a change in resistance will cause a change in voltage. And as temperature changes the resistance of material, we can measure the voltage to tell the temperature. We will use a material like platinum, which has a near linear resistance to this temperature gradient. We test the material again at known temperatures to attain the graph. For example, at 0 degrees Celsius, the material will have a resistance of 100 ohms. And at around 100 degrees Celsius, it will have a resistance of 138.5 ohms. There are some different designs for these types, but they're typically either film type, where the platinum is coated onto a ceramic plate into a pattern and then the whole thing is sealed in glass, or it will be a platinum wire, which is wound around a ceramic core. Again, this will be sealed in glass for protection. Thermistors. Thermistors have a few variations in design, but these two are fairly common, the flexible version and the more rugged fixed version. A thermistor is just a thermal resistor, meaning it's an electrical resistor which changes resistance with temperature. But there are two types of thermistors, the NTC or negative temperature coefficient and the PTC, the positive temperature coefficient. We saw earlier that the resistance of a metal typically increases as its temperature increases. And that was because the atoms started to vibrate, which makes it harder for an electron to flow through the material without colliding. The PTC type thermistor behaves something like this. We call it positive because if we plotted the resistance with temperature, then we get an upward trend showing an increase in resistance with temperature. The other type is the NTC, or negative temperature coefficient. With this type, we use a semiconductor which behaves a little differently. As you might guess, we call it a negative temperature coefficient because when we plot the resistance of temperature, this type will actually decrease in resistance. This is to do with the structure of the atom of the material. If we look at a simplified atom of a metal, we have the nucleus at the center and then a number of electrons all on different orbital shells. A conductor has 1 to 3 electrons in its outermost or valence shell. Each shell holds a maximum number of electrons, and an electron has to have a certain amount of energy to be accepted into each shell. The electrons farthest away from the nucleus have the most energy. We need electrons to be able to move between other atoms in a material for it to carry electricity. Electrons are held in place by the nucleus, but if they can reach the conduction band, then they can break free and move. With a metal atom, the conduction band and the valence shell overlap, so it's very easy for an electron to become free and move. With an insulator, the outermost valence shell is packed. There's very little to no room for an electron to join. The nucleus has a tight grip on the electrons and the conduction band is far away, so the electrons can't reach this and escape. Therefore, electricity can't flow through this material. However, with a semiconductor, there's one too many electrons in the outer shell for it to be a conductor, so it will behave as an insulator. But as the conduction band is quite close, if we heat the material up, some electrons will gain enough energy to make the jump and break free from the atom. As more heat is added, more electrons move from more atoms, and so the material's resistance decreases. So its basic construction is just a piece of semiconductor between two conductors, and this is sealed with a protective coating. So, which one is better? Well, they all have different pros and cons. There is no perfect fit. It all depends on what you need the temperature sensor for. Consider that these are used for everything from water, steam, air, gas, refrigerants, and oil. And they're installed everywhere from engines, air conditioning systems, air compressors, heating systems, hydraulic